but I'll try to talk about the level I'll talk, I think, in the lecture, so we can adjust the sound. Okay.
The third course of this summer school on numerical hydrodynamics, and we have a world expert on university hydrodynamics, Professor David Neilsen from Brigham University.
Okay, thank you. I hope you had a good weekend after the very strenuous week and rested for another round. I'm very happy to be here and excited to be here, and appreciate everyone being here and being excited, and I think we'll have a good time. Before I begin, I'd just like to ask very quickly, how many of you have had a course in fluid mechanics before? So is that what, roughly half or so? I just wanted to ask because in the United States, it's not a usual topic for undergraduate physics majors. And so when I first started doing this research, I was completely lost. My dissertation advisor gave me this problem with fluid mechanics, and he didn't really know anything about fluid mechanics, and so it was a pretty tough learning curve. And so in preparing these lectures, I hope to get you going in at least in the right direction, so that you can have a simpler beginning. Let me just tell you a little bit about our goals for today, so we can see how far. I don't know how far we'll get, but I'd like to begin with what a fluid is. Introduce the fluid equations. I'm not really going to derive them, but we'll at least see what the important quantities are and discuss that. I want to discuss why they're useful. A little bit about equations of state. And finally, there are two important solutions. I think we'll only get to one today, but we'll look at a star solution. If we get all of that done, we'll be lucky. So let's start with what a fluid is. So actually, let me start off a little bit. Let me just start off here and say a fluid is an extremely useful model in astrophysics. And if you look through the astrophysical literature, you'll see that fluids are used to describe neutron stars, white dwarfs, other stars, I won't list them, say accretion disks, the interstellar medium, cosmological fluids, the radiation fluid, the matter, and cosmology. A fluid is used to describe all of these things. And if you think about the range of densities here, it's amazing that there's one model, the fluid, that covers all of these, because neutron stars have densities 10 to the 14 grams per centimeters cubed. White dwarfs might be around 10 to the 6 grams per centimeter cubed. Accretion disks, we're down to maybe 10 to the minus 8. When we go to the interstellar medium, we start usually not talking about densities, but just number of particles per cubic centimeter. And we might have 10 to the 8th atoms per cubic centimeter. If you look at the standard cosmological model, the density, average density of matter in the universe today is like 10 to the minus 29 grams per centimeters cubed. So if you look at this range, it's fascinating that there's one model that is used continually here. So let's talk a bit about what fluid, and then we want to hit, why is there one model that covers this extreme range of 45 orders of magnitude almost of density. Fluid equations, how would you describe what a fluid is? Anybody? How would you describe what a fluid is in physics? Any guesses? It's not a solid, right? Solids have strong intermolecular bonds, kind of fixed bond lengths. So a fluid isn't that. What would it be? I'm sorry, could you say that? Okay, yeah, so we have something like the Navier-Stokes equations. What we have are a whole bunch of point particles that are moving around. So it's a many-bodied description, right? So we have many bodies. We have a fairly large mean free path between particles. So we don't have, maybe the mean free path is roughly 10 times the average molecular size or atomic size. In a fluid, we have to have lots of particles because we're basically going to use locally thermodynamic equilibrium to describe this many-body system, right? So I have 10 to the 23 particles. I have many, many degrees of freedom. But if locally they're all in thermodynamic equilibrium, then suddenly I can use just a few state variables to describe this. Things like density, things like temperature, okay? The other important thing is that the fluid is the simplest model, I think, although maybe I shouldn't say simplest, but it's certainly a simple model where globally, or on large scales, it's not in equilibrium. And this allows me now to study systems that are not in thermodynamic equilibrium, say, you know, boiling water, where I apply heat from the bottom. The heat causes the fluid at the bottom of the pan to rise to the top, and I get convection cells. I can describe all this non-equilibrium system with fluid mechanics. The important thing here is that when I have collisions between particles, and I have many particles here, when I have these collisions, any quantity that isn't conserved in these collisions will quickly decay or average out to be zero. Quantities that are conserved in microphysical collisions, things like energy and momentum and particle number, these are the important quantities that will be conserved and can be out of equilibrium even on a large scale. And so when we start building our physical model here, we're going to have basically two different types of variables. I have variables that are going to represent conserved quantities. These are the quantities conserved at the microphysical scale. And these are the quantities that can be out of equilibrium in the system. And these are things like energy and momentum, particle number. Now, I'm going to assume that we don't have nuclear reactions going on. And so when I talk about particle number, I'm always going to be thinking of baryon number being conserved. If we allow nuclear reactions to go on, then we just have to expand what we mean by this a little bit, and we start then tracking particles and leptons, and we're using some laws of particle physics to sort that out. But these are things that can be conserved at the microphysical level, also at the macrophysical level, the fluid level. In addition, because I'm using thermodynamics to describe my fluid, I'm going to have some variables that come from thermodynamics. Now, this word that I'm going to describe these as primitive variables doesn't mean that they're somehow less important, but it's the terminology that's arisen in the numerical computation of fluid dynamics to distinguish these two types of variables. These variables I think of often as the kind of the thermodynamic variables, and so we have things like density and pressure, temperature, what else? Here I have momentum, here I have velocity. I'll write that down here because I'll need that later. I feel like I'm missing something. Density, pressure, temperature, oh, internal energy, there we go. I'm writing all of these out because I'm going to need to introduce a lot of variable names here. And because we're doing relativity, we have to be careful about our variable names and what they mean. And so I want to get them kind of all down in one place so you can refer back to it. For the energy, I'm going to use a capital E. And I'll sometimes use tau, but we'll come to that later. For the momentum, I'm going to use a capital S. And in relativity, I'm going to put an index I down, or this will be, so this is a one form that we'll come to. For particle number, I'll use capital N. And when I talk about a particle number density, I'll use little n. if I can write more clearly. When I think about the density of the fluid, I'm going to use rho 0, and this will represent the rest energy density, the energy density in the rest frame. Pressure will be easy. We'll use capital P for that, capital T for temperature. Those are simple ones. For the velocity, we'll use V. I'll usually write it with index up, meaning it's a vector. Energy. This is where we have to be a little more careful in relativity because we're going to have different energies to worry about. What is the internal energy in a fluid? The internal energy, if we think about our thermodynamics, is the energy that the fluid has because the microphysical particles have velocities and are moving around. And it doesn't necessarily represent energy due to motion on the large macroscopic scale. So when I talk about internal energy, that's what I mean. I'm wondering how, anyway. So internal energy, the variable that we use is actually called the specific internal energy. This means internal energy per unit mass. And that variable I'll use is epsilon, so that the total internal energy is going to be rho naught times epsilon. So those are some of these choices of variable names just come from the literature and the common use. So it seems a little bit odd to use a product of two symbols for the internal energy, but anyway. Let me see. There's one more thing. The energy here I wrote as capital E. I will use that actually as something else. I'm sorry. I'm going to write this as a script or as a variable. In LaTeX, it's called var epsilon. That's what I want to call it. It's also an epsilon, okay? The capital E is what I'm going to use as the ADM energy. I forgot to. I'm getting my energies mixed up already. You can see how important it is to be careful. This is going to be my energy density, actually. So this is a density. The other quantity I'm going to introduce is rho, which is the total mass density. And it's going to be rho is epsilon over c squared. So you just take the total energy, divide by c squared. That gives me an effective total mass density. And then I'm going to say that rho is rho naught plus rho 0 epsilon. So total mass density is equal to the rest mass density plus the internal energy density. So those are the sums of variables here that make some of this confusing. Okay. So we talked about this fluid here. Let's make a picture. Imagine I have this system. I've got little particles moving around inside. Okay, they have fairly large separation. It means they have a large mean free path. I imagine taking some volume in here. And this volume is I'm going to call this my control volume, or fluid cell, whatever you want to call it. And this is the scale at which I'm doing my thermodynamics. Okay, I want inside this volume the particles to be in thermodynamic equilibrium. And I can look at this volume here and I can count the number of particles and I can get a number density. I can measure their masses and calculate a density. I can calculate a pressure, a temperature, all assuming that I have some local thermodynamic equilibrium. Now, as these particles move around, we could imagine two scenarios here. I don't know a good way to draw this, but imagine that these particles are all moving around in different ways. We could imagine now looking at this system at a later time, and if my volume follows all of the particles, then maybe I draw a new volume that looks like this. Oops, got to keep that guy out. Well, we'll make him go in. How about that? He goes inward. Okay. So I have an original volume here. I'll maybe draw that with a solid line. And then if I track the particles like this, then this is my new volume at a slightly later time. Okay? So I'm basically following the particles around. My volume is changing with the particles.
So you're conserving the number of particles in the volume?
That's right. So the number of particles in the volume is the same. The volume is changing in size and moving around with the particles. Hmm? They may not be in equilibrium later on. We're going to assume that there is locally always this equilibrium. I'll mention that in a moment. If I allow my volume to move around like this, that's called the Lagrangian description of the fluid variables. So the volume moves with particles. Now my other choice is just to keep the volume fixed and not let it move around. Okay? And if I do that, that's called the Eulerian description. So this, you know, the Eulerian description, I have a coordinate system and I just fix my volumes to the coordinates and they never change. And as the fluid particles move around, I maybe have to continually calculate the density, count again how many particles are in there. This is the description that we're going to use. This is the one that is often used. Both of them are very useful. Some things are easier to prove in the Lagrangian description. Some things are easier to use with Eulerian. In research level, relativistic hydrodynamics, both of them are used. The nice thing about the Lagrangian description is that if you have very fine features, so you have a very strong relativistic shock, it's maybe generating some turbulence, it's maybe I'm modeling a shock going through the interstellar medium or through an accretion disk. Sometimes the Lagrangian description is useful because I keep my particles, it's easier, it basically gives me a nice way to have the grid refined to where things are interesting in the fluid, because I always keep the same number of fluid particles in a cell. The nice thing about the Eulerian description is it's very simple to set up with coordinates, and that's what most of the runs use today are Eulerian version of fluid mechanics. Okay, we're going to assume that I always have enough particles in here that it's in thermodynamic, that I have a thermodynamic equilibrium. This is called the continuum hypothesis. The continuum hypothesis.
What is the continuum hypothesis? I missed you.
Oh, I just said so far its name, I haven't just said what it is. The continuum hypothesis is this. It basically says that I have enough particles that I can make these control volumes squeeze down as arbitrarily small and still have a thermodynamic equilibrium. Okay, so this is basically saying that I can take these control volumes and turn them into points so that I have a true continuum, and that when I write down rho and p and t, these are now functions of like x and t. So they're true functions over the real number, over the real domain. So that's the continuum hypothesis, that I can always shrink these down to 0. If the continuum hypothesis fails, then of course the entire model here is going to fail. Because we need thermodynamics to do this. If we don't have thermodynamics, then we have to move on to transport problems from statistical mechanics and start thinking of things like the Vlasov equation or the Boltzmann equation or something more complicated. So in relativistic fluid mechanics, it actually isn't hard for this to fail. But what I mean by that is we have densities that might go to 0, and so we have to put in some kludges in our code to make that not happen. But that's another story. Anyway, so that's a little bit about the fluid model. hopefully, just so we have a kind of a physical sense of the model that we're going to use. Eraser. Oh, here these are the erasers. So let me grab an eraser here. I think I'll. Mm-hmm.
Related question. In cosmology, since the density is very less, it's 10 to the power minus 29, so it's almost like zero. That's why we use Boltzmann equation and all those things. We don't use continuum hypothesis.
Yeah. Well, I mean, when we do our very simple cosmologies, though, we still use the fluid for evolving, the density to today. But you're right. If we're really trying to evolve this in a quantitative, more accurate way, we would have to do something else. For example, there's a person in my department who is trying to model very carefully what happens in a mass spectrometer. In a mass spectrometer, you have a sample that you heat up, and you have some coils to accelerate the particles into an evacuated chamber where they have a magnetic field so you can measure the mass. If you want to be have a very accurate model of what happens as these particles go through this nozzle and into the chamber, you have to do something else, something more complicated. About what our fluid equations are. So we've talked about what the fluid is. Now let's introduce the fluid equations. As I said, the aspects of our system that are going to persist, the things that are the quantities that are not in equilibrium that will persist through lots of microphysical collisions, are things that are conserved. And so it's not surprising that my fluid equations are basically going to be conservation equations for energy and momentum and particle number. So we're going to have kind of three sets of equations. I want to show you a little bit about how this goes. And I think what I will use is a simple example. By the way, these are called balance laws sometimes. I'll show you a little bit what I mean. Or in a special case, they're called conservation laws. So our idea here is I know that I have these conserved quantities like energy and momentum. I'm going to write down equations that describe how these quantities change in time. And I'm looking at some type of a balance between, well, you'll see how this goes. So what I'm going to do is I'm going to think of something that's conserved. Let's choose particle number. So I have total particle numbers conserved in my fluid volume. I'm actually thinking of a Lagrangian description here. So I'm going to allow my fluid volume to change in time. And I know that this is total particle number. This is something that should be conserved. And the total particle number can be written in terms of a density, which I'll write as little n. So I just take the number density, I integrate over the volume, that gives me the total particle number. As I said, this volume can change in time. Okay? Now what I'd like to do is find an equation for how total particle number changes in time. So I need to differentiate this volume here. Okay, this is where a little chalkboard math is going to come in and help me, because I'm not going to do all the steps here. Let me make that clearer. Okay, so I have total particle number. I'm differentiating with time. So the total particle number is just this integral here, this density, the integral over a density. And I have the time derivative out here. Now, I want to move this time derivative inside the integral. When I do that, I get this extra term right here. This extra term comes from taking this, it basically comes from the fact that my volume is changing in time. So it comes from, when I differentiate this, I can imagine differentiating the little n and also then differentiating a Jacobian that tells me how the volume transforms in time. And that's this extra term here. This v here is the velocity. Now, whenever I talk about the velocity of a fluid, I'm not talking about the velocity of individual particles here. I'm talking about the velocity of the entire volume, control volume, as it moves around. So that's what I mean by the velocity. Sometimes people call this entire control volume a fluid particle. Right? In our continuum hypothesis, we assume I can shrink this down to a point size, and then I imagine how this fluid volume is moving around. That's our velocity. Okay? And then I'm putting a little t here as a subscript just to remind myself that this volume that I'm integrating over is changing in time. Okay, so this is the equation for conservation. Now, if my particle number is conserved, I don't expect this to change at all, and so I'm going to put a 0 there because I'm not creating or destroying particles. This is a total time derivative, and you've seen this before, that this total time derivative can be sometimes called a convective derivative, and I can rewrite this as v dot grad, right? This is my convective derivative. So I'm going to put that in here. I should have, let's see, plus v dot grad n plus n divergence of v. And I see that and the right-hand side was 0, so all of that is equal to 0. And so I can combine those last two terms as divergence of n multiplied by v. Now, at that point, you probably all recognize this equation as what's called the continuity equation, right? And you realize and you know that you've seen this. We kind of often think of this, if I now go to an Eulerian description, I imagine that this tells me how the number of particles changes as I have a flux of particles through the boundary of the box, right? Now, this is the classical continuity equation. If I go to relativity now, the only thing I need to worry about is the fact that the volume gets modified by the Lorentz factor. And so I'm going to make two changes here. First of all, I'm going to assume that all these particles have the same mass, so that there's this interesting simple relationship between number density and mass density. And then I'm going to define a new variable. This W here is the Lorentz factor, the usual Lorentz factor that you see in special relativity. And this is the relativistic density. So the Lorentz factor accounts for the change in volume. One dimension gets scaled by the Lorentz factor. And then this is the relativistic form of the continuity equation. And this is actually one of our fluid equations. Okay? So that at least gives you kind of a simple idea of how we derive these equations. We're using conservation laws. And we could go on and look at the momentum equation. I don't think I'll do all of it, but I could imagine now thinking of a total momentum, and my volume is conserved. And let me just say the total momentum is a integral over a little p, which is a momentum density. Actually, let me use S. I have a momentum density S, and I'm going to integrate to get the total momentum. I now write down how does the momentum change in time. Now, the momentum could change in time, right? because this fluid particle could be moving faster or slower at one point or another. That's unlike this case where we knew that mass was conserved. How could the momentum change? Well, I can have forces acting on this. And so instead of the right hand being simply equal to 0, I have to consider the fact that there could be body forces, external body forces. When you do this in classical mechanics, you usually consider gravity. This is some force, external force, that's acting on the particles in the volume, like gravity. And then I also have surface forces. I may have some force on the surface. Now this term is important because these fluid cells exert pressure on one another. There might be another fluid cell up here. There's a pressure, force per unit area on these cells, and that's where the pressure term comes in. And I'm not going to go through and derive all of that, but in classical physics, this equation becomes that. Okay, just a point of definition. For whatever reason, when I have these conserved quantities and I have things on the right-hand side, sources, these are called balance equations. When the sources are all 0, like in this case, they're called conservation equations. It's not a big distinction, and in relativity, almost all of, with general relativity, with the geometric terms that we have to worry about, we almost always have balance equations, but we often get sloppy and just call them conservation equations anyway. But there is a distinction. The final equation would be one for energy. I don't think I'll write that down, but we would look at how the energy changes. So this is like an outer product of two vectors. So it's like rank 2 object. In classical physics, they often just write it something like this. In relativity, we'll write it with indices. But it's like an outer product of two vectors. So that when I take the divergence, I have a vector left over. Where normally the divergence of just a vector is a scalar. Does that make sense? Okay.
It contracts with the graph contracts with the V index, is it?
Yes, I think so. I think that is correct. It's an outer product. So it's something in classical physics would be like that. It's a rank 2 object. Mm-hmm.
S is the momentum density?
S is the momentum density, yeah, and V is the velocity. The energy equation, I'm not going to write down out of interest of time, but when we think about how energy is conserved, we know it's conserved, but again, there will be some balance terms because we'll have to think about what happens as, when the volume changes, I'm doing work, right? PdV work on the system, and so that will be a source or sink of energy. And then if I have any viscosity or heat conduction, I have to worry about that. But I will just go on for that. I think the main thing is I wanted you to kind of see where these fluid equations come from, the fact that we're using conservation laws, the conserved quantities, to define the evolution equations for the fluid. There's one more piece of information that we need. Mm-hmm. What is V? Grad P, the pressure. This is the gradient of the pressure. So that's representing the forces, the body force between fluid particles is where that term comes from.
So the vector P is the momentum and the P without a vector is the pressure and the big...
Oh my gosh, yeah. You can see it's a nightmare trying to keep these things straight.
Big V is volume and small V.
Yeah, I should have used a small p somewhere. It's too late now, isn't it? But I forgot that I had two p's that I was writing as capital letters. You'll notice that as we go through this, the notation can be really complex because you have standard variables in GR, you have standard variables in thermodynamics, and standard variables in, I don't know, fluids, whatever. So I'm using W for the Lorentz factor because gamma is taken by something else. Gamma is going to be in my equation of state. And I'm going to use a capital gamma there because my little gamma is from GR in the ADM decomposition of the metric. And so it's actually a challenge to come up with names that are the same. Okay. If you remember the list, I had a list of conserved variables and a list of primitive variables. And the conserved variables are things that I'm going to have equations for. And I also had some other variables that were like density, pressure, temperature, these, some thermodynamic variables. And if you looked at the two lists, you'll notice that there were more primitive variables than conserved variables. My equations are only from the conserved quantities. And so I need some additional information here that tells me how to calculate the extra primitive variables. If for example, I counted them, I have 3 equations here, right? Because this is a vector equation. I have 1 equation here, and I have 1 more from energy. That's 5 conserved quantities that I'm basically following. And if I look at the conserved or the primitive variables, I had 3 components of velocity. I had a density, I had a pressure. That's 5. But in addition, I had temperature and internal energy. I had at least 2 more. And so I need some additional information to close the system so that make sure I can find everything I need. And that comes from what's called the equation of state.
So we have 6 equations because we have the continuity equation also.
So this is 1. Yeah. Yeah, and I have 1, and I also have 1 for energy, and then the 3 here. The equation of state comes from thermodynamics. And this is, we could go through and talk about what it is exactly. There's there you can define different equations of state. I think I'm not going to talk about that in a lot of detail, except to say this. We are going to use the simplest equation of state for our purposes. Is going to be the ideal fluid. That's what we call it because it's really the ideal gas model. In the ideal gas model, I have an equation like this. That K there is Boltzmann's constant, right? PV equals NKT. I also have an equation for the energy of the ideal gas. F here would be the number of degrees of freedom. And each degree of freedom that's in the Lagrangian, every squared term in the Lagrangian has a degree of freedom. And so for a monatomic gas, F is 3. I have 3 linear components of velocity and so on. Anyway, this is my energy. Now, if both of these equations are functions of temperature on the right-hand side, if I had an equation for temperature, they would be really easy to use, but I don't. The equations that I have are things for like energy. And V here can be written as 1 over the density, right, with some constants. And so what I need to do is actually combine these two together to eliminate the temperature. And that gives me an equation of state that I can use in my evolutions. And that equation of state looks like this. Shouldn't have erased my list of what to talk about. If I combine these together, and I have to worry about some constants factors, I get this equation of state in this form here. So this is my ideal fluid equation of state written in a slightly different way. It's also called a gamma law gas, because this capital gamma here tells me something about the particular fluid. The capital gamma is the ratio of the heat capacity at constant pressure to the heat capacity at constant volume. As you remember, the number on top is bigger because when you work at constant pressure, you have to do work again to maintain pressure, constant pressure. And so gamma is a number bigger than 1, okay? For our purposes, gamma will be in this range. And this constraint comes from the speed of light. The speed of light, or I'm sorry, the speed of sound for this equation of state is simply gamma minus 1, right? Is that right? No, I'm confused. Let's see, this is the speed of sound squared, I think. Is gamma minus 1 in units where c is equal to 1. And so if I want this sound speed to be bounded by the speed of light, then gamma can be at most 2. And it's bigger than 1. So that's the equation of state we'll kind of have in our minds. You can come up with more complicated equations of state for different things, but we'll be using just the ideal fluid equation of state. Let's see, we go till 11, right? Is this a good time for a break? Okay, I just want to make one more comment and then we'll take a break here. I just want to pause, and if you remember at the very beginning, I listed here a bunch of models that fluids are used in, and I said, isn't it amazing that over this wide range of densities, you have one model that covers it all? Okay, the secret for why that really works is this. The equation of state, where does it come from? The equation of state is my microphysics. This is where I plug in specific microphysics, is right here. Everything else is just a conservation law. So if I have, ideal gas particles, non-interacting particles, I can use the ideal fluid. If I want to think about a realistic equation of state for a star, then I have to think about nuclear physics, and I have to think about compositions and more complicated things. And I might have a more complicated equation of state, but I can plug it into these same conservation equations. And so this is really the secret of what makes the fluid useful, is I can adjust the equation of state to match the microphysics that I want to model. And so we'll just stop there now and take a break for a few minutes and let everybody, let your minds relax a little bit, and then we'll come back and go from there. And I'll think of some references that I can tell you where parts of it come from. Okay, I think we're ready to start again. So we've looked at the way we derive the fluid equations with Newtonian physics and hopefully build some intuition. The important thing here was that we're using conservation laws or conserved quantities to build our equations of motion for the fluid. Now we want to think about how to do this with relativity. Oh, I forgot one more. Let me pause there and go back over here. There's one more thing I want to say about the equation of state, and if I don't say it now, I probably will forget. This version of the equation of state, where the internal energy density is related to the pressure, this is, I'm going to say, is always valid for the ideal fluid. So if you have an ideal fluid, this is the general form of the equation of state. Now, if I look at the first law of thermodynamics, and if I say that the entropy is constant, so this is a reversible process, then I can rewrite this equation of state in a different form called a polytrope. And that looks like this. And this is an equation, a form of the equation of state you probably have seen often. Okay. Now I'm going to, this k is a constant, right? And gamma is a constant. It's called the adiabatic exponent. I'm going to put here explicitly that there's an S. This is not the S of momentum. This is the S of entropy. But I'm writing K as a function of entropy because it reminds me that this K is only constant if the entropy is constant. I want to remind you of this, to kind of point that out, because when we talk about fluid mechanics and evolutions of fluids, an important thing happens we'll talk about probably tomorrow, is that we can have shocks that occur. So shocks are these discontinuous solutions where I have a discontinuity that propagates in a direction. The shock here is a compressive solution. And it is because I have characteristics that essentially cross that cause this shock to occur. That's what we'll talk about tomorrow. This is an irreversible process. I can't propagate backwards in time. And so when a shock occurs, I have an increase in the entropy. So I cannot use this form of the equation of state in the evolution. I have to use this. Now, when we work with setting initial data for our stars, this afternoon we're going to look at simple spherical star solution. We can imagine that our star is beginning its light. Well, we're thinking of a star that's in equilibrium. It's in thermodynamic equilibrium. The temperature is constant. The entropy is constant. Then we can build our star solutions using the polytropic form of the equation of state. And that's what we will do when we look at the stars. Okay, so, but just kind of if you start doing relativistic fluid mechanics, often our initial data is constructed with this, but our evolutions in time where we have shocks, we're going to use that form of the equation of state.
So is there a simple explanation? So what happens if you use the polytrope during the evolution?
That's a very good question. So it's a bad, well, okay, if you use a polytrope in the evolution, you can, as long as you have nothing that's irreversible, no change in entropy, no shock. If you do have a shock that occurs, so this is, I said at the beginning I started fluid mechanics kind of on my own, and I was just trying to read the primary literature, and it actually took me 2 or 3 weeks to find that this was the equation of state I really needed to use. And the very first fluid code I wrote used that one. And I started off evolving something, and as soon as a shock appeared, my shock would split up into 2. And so it's clearly an unphysical result that you get when you do that. And so you'll get the wrong answer, essentially. There are some people who evolve with this, and they are wrong. They don't anymore, luckily.
No names.
No names.
So gamma depends on the microscopics of the fluid.
Yes. And often people will, when you even have a complicated nuclear equation of state, now you're thinking about a real complicated nuclear microphysical model for your nuclear physics, then gamma could actually be a function of rho as well. And you'll see people, they'll plot rho and they'll plot gamma, and you'll get something that drops down when you have neutron drip and then goes back up, and you'll get some complicated function there for gamma. We'll just assume that gamma is a constant. But yeah, there's some microphysics in the choice of gamma, because gamma is this ratio of specific heats. So in a simple model, yes, you're correct. If it's just in a simple ideal gas, it depends only on the number of degrees of freedom, and it's constant. But when you have a more complicated nuclear physics model, what people will do is they will essentially fit. You have some very complicated model with lots of things going in, compositions, number of ratio of neutrons and protons, which will vary with temperature, and other things that happen. And what you get out, you basically fit to just peak to this form, and then you'll let these two things vary with density, just so that you have a simple analytic form for your equation of state. Okay, I started off saying that we're going to look now at relativity. There are different ways you can introduce the stress energy tensor for a fluid in relativity. I'm going to use a simple one that's just motivated by thinking first of dust. Dust is what we call a fluid if the pressure is identically zero. So we think of these as just particles with that have no pressure at all. It's a common model for stars in the galaxy, right? Stars in the galaxy don't exert a pressure on one another as they move around. And so if P is zero, pressure is zero, we call that a special case of dust, okay? If I imagine I have my system and I've got these little particles that move around, there's not much I can use to think about to characterize this. I could characterize it by a rest mass density, you know, number of particles per unit volume multiplied by a mass, which I'll assume is the same. I know that these particles all have a 4 velocity. I'll use U for the 4 velocity. And that's about it. There's really nothing else I can use to describe this system. So I now need to think about a stress energy tensor, T, not the temperature, of course, but T with 2 indices here. A stress energy tensor tells me about the energy, the momentum, and the internal stresses in the system. This is a rank 2 object, and it has to be covariant. That means that it has to have some form that no matter what coordinate system I'm in, it always contains the same information. And I'm going to build this covariant rank 2 quantity out of the only things that I have to work with, which is a vector, 4 velocity is a covariant object, and I have a scalar that's also a covariant object. And about the only way I can do that, to take these two things and build a rank 2 object out of all of them, is to do something like this, where I have a product of the density and the two 4 velocities together. This is now a rank 2 object. It's going to be covariant because it's built out of covariant objects, vectors and scalars. Okay? And this is indeed the stress energy tensor for dust. So this is dust. Now, when I go to a fluid, I'm going to make the pressure not zero. And I have to imagine what can change. Okay? So now I think about the fluid. P is not zero now. But I still have the same things. I have densities. I have 4 velocities for these particles. If I think about the rest frame, so I go into the rest frame of this fluid. And I think, what should this look like? Well, I have to know a little bit about the stress energy tensor. The spatial components of the stress energy tensor are called what we call in classical physics just the stress tensor. And that tells me about forces between different directions. If I'm in the rest frame of this fluid, well, I guess I have to imagine what I should see. I better think about what the fluid is. So I better specify here that I'm thinking of what's called a perfect fluid. Okay, I'm thinking of a fluid here that has no viscosity. I'm thinking of a fluid that in its rest frame is isotropic. So it is the same in every direction. And there are no shear forces. So shear forces are, if I imagine my different fluid control volumes, are forces that are tangential to the boundaries. Okay, I'm not going to allow that to happen. So the only forces that can be exerted between two different fluid particles or two fluid control volumes are pressures that are normal to their direction. Okay? So if I go into the rest frame of this fluid and I think about what the spatial part of this stress energy tensor should look like, I should get basically P on the diagonal, because every direction looks the same. And the only forces that I'm allowing are the normal pressure forces between fluid particles. The top row and column here of this stress energy tensor, I have 4 things. The top row and column basically this is in the rest frame, this would be the energy, and then the momentum down the 3 momentum on the spatial part here. And so I have no momentum, so I'm going to put zeros there. And then I want the energy density right there. Okay? And so I look at the form of the, I'm thinking of special relativity, just the rest frame of the fluid to kind of motivate the form of what it should look like. I kind of come back up here and think, okay, how can I go from this to now adding in pressure? And the simple result is that for the perfect fluid, I have this. Epsilon here is the total energy density of the fluid, and this is the pressure, the 4 velocity, the pressure, and the metric. So,
Why are conditions 1 and 3 different?
I think of this one as basic. They're really not really different. Maybe I should have said here no heat flow between different. There's no heat that goes from one cell to the other. Okay. It's possible to put C's in, but I don't think I'll do that. We'll just leave it there. So that's my stress energies tensor for the perfect fluid. I don't know what to do here. Let's see. I think I'll go ahead and talk about the 3+1 form of the equations. I have the stress energy tensor here. The equations of motion, as you know, are these. So once I have my fluid model, I come up with the stress energy tensor. Then the equations of motion for the matter or the energy or the whatever, the fluid in this case, are the divergence is equal to 0. So that gives me my equations of motion. What do these equations represent? Well, I basically have an equation for the energy and an equation for the momentum that come from this.
So you introduce a metric now, then, TAB.
Yeah.
Is it obvious how it comes?
Is it obvious how it comes in? If you wave your hands, so what you do is you basically say, I want to have this form in special relativity, okay? And I think about, okay, what could I build to do that? Well, if I'm in the rest frame of the fluid, then the U would look simply like 1, 0, 0, 0. And so when I have a term like this, that would give me the epsilon up here. And I think, okay, how do I get the pressure here? Pressure is a scalar number here, but I need it on the diagonal here. But one thing I can multiply by is like the identity matrix. Or in special relativity, that would actually be the metric, eta. And so I might imagine doing something like this. And that would give me, eta would give me the PPP right here. The only problem is that eta also has a -1 up here. And so I'd have an epsilon minus P. But I don't want that to happen, so I'm going to add a P in with UA, UB, so that gets canceled out, and then I get this form here.
You generalize this for any space-time.
Yeah. Exactly. So now that I've built this out of, I've gotten to one very specific frame to construct the T, but because I've used covariant quantities, we just say this is the fluid. If I let P go to 0, we call it dust. We imagine particles, fluid particles that don't interact at all. And so where you might see this is in modeling a cluster of galaxies or a cluster of stars. I have density there. I have mass, but the stars, if one cluster goes through another, they don't exert a pressure or force on one another. And so that's like dust. That's an astrophysical application of that. But the name is really just kind of by definition. It's just what it's called, as far as I know. Okay. We have the fluid equations here. We could do a couple things, and we were so short of time that I don't know what to, let's see. You can, if you look in your GR books, so what they'll normally do is they'll take this equation and they'll project it along the 4 velocity of the fluid and perpendicular to the 4 velocity of the fluid. And what you come up with are basically equations that reduce to the classical Newtonian fluid equations. You'll get something like the continuity equation, you'll get something like, or the energy equation, you'll get something like the Euler equation for the momentum. We're interested in numerical relativity, and so it makes sense for us just to kind of jump ahead and talk about the 3+1 decomposition of these equations. And I think that actually I'm going to save that for tomorrow. I want to talk a little bit. We have only about 20 minutes left. And I want to talk a little bit about our first solution that we're going to do this afternoon in the tutorial. And we want to think about building a star. Okay? So we're going to just pretend that we all know what the equations are. And Thomas has shown us how to take these quantities and project them, normal and perpendicular. I'll show you a little bit about that tomorrow. But let's just pretend that we did that. And now what we want to do is think about solving a star in general relativity. So I have the Einstein tensor. I set it equal to the stress energy tensor with some factors there. That gives me the Einstein equations, okay? Then I have a second set of equations. These are the fluid equations. So I have 2 coupled sets of equations to solve. Now when I build a star, I'm going to make a lot of simplifications. I'm going to assume that I have a spherical star. I'm going to assume that it's static. That means no time dependence at all. That's already a big simplification, right? We have, that's going to simplify the fluid equation, or these 2 sets of equations a lot by going to spherical symmetry, taking all the time dependence out of the problem. When I do that, I come up with a set of equations. If I take these 2 assumptions and I think about the most general space-time that I could write down, that both is spherically symmetric and static, I come up with a space-time that looks like this. So choosing a particular way to write the angles. This is the most, using anyway, wise choice of coordinates, the most general way that I can write down a spherically symmetric space-time that is static. So I have a function here, capital phi. It depends only on r. I've written this term in a suggestive way with a little m that is also a function of r. And then I have the angular part here for spherically symmetric space-time. The final thing I'm going to demand for the star is, of course, I know from relativity I'm going to imagine that I have if I have R here, and let's say plot the density of the star here, I'm going to get some profile like that, right? So I'm going to have a density that's large in the center, and as I integrate out, it's going to go down to 0. At this point here, I'm going to match onto a vacuum space-time that's also static and spherically symmetric. And you know from your relativity class probably that there's only one space-time that matches that. That's the Schwarzschild space-time that's vacuum, static, and spherically symmetric. So we will match this to Schwarzschild space-time. And that's part of the magic of choosing this term to look a little bit like what you expect for Schwarzschild. If I now take this guess or form of the metric and I put it into the Einstein equations and the fluid evolution equations, and I expand everything out, I come up with equations that look like this. There's some simplifications that have gone here. I'm not going to write that one down right now. Okay, I have 4 equations. This one actually comes, this is the continuity equation, right? This is the extra one. I wrote that one down. But one equation is for M, one equation is for P. Okay, this one is from the GR equations, this is the GR equations, this is from the fluid equations, and this is the continuity equation. I put a couple C's in. Well, anyway. I don't have all the G's and C's in, so let me just erase that because I haven't been consistent. I wanted to emphasize, this is the energy density, not the mass density. But C and G are one here. This is a set of equations that I have. This is called the Oppenheimer-Volkoff equation right here. From Oppenheimer and Volkoff, who wrote the paper in 1939, I think, on this. And sometimes the whole set are called the TOV equations for Tolman, who did some work in this equation right here. Oh, the third equation. This is for this function here. And people usually don't worry about it. And so I didn't write it down, but I'll give you a sheet this afternoon that will have that equation on there. But it comes from the Einstein equations.
Which conservation law it implies? It implies which conservation law, just like the others have some kind of...
Oh, some kind of conservation. It's really a geometric equation. It comes from the Einstein equations, and it's a geometric equation. It comes from the time component of the Einstein tensor equation. Okay, so this is a set of equations to describe our star. Notice that P, dPdr, has a minus sign here, so pressure has a negative derivative as you go out in radius. That makes sense, right? As I think about the profile of the star, I should have a high pressure at the center of the star. It goes down as I go out. This equation here looks almost like a Newtonian equation, right? It's M here, and I have energy density here. And our interpretation of the function M is that M, R, tells me the mass contained inside radius R. So as I integrate out, if I write it in integral form, I integrate out to R, and I'm going to have a 4 pi r squared rho dr, whatever like this, something like this. And so for any radius r I choose, this tells me mass contained within the shell of radius r. That's how we interpret m.
So are we assuming that energy density is constant over the entire?
No, no, it will vary. I have an equation for m, right? When I see m on the right-hand side, I have an equation that tells me how m changes with r. I've got an equation, so I got p on the right-hand side. I've got an equation for p that tells me how p varies with r. Phi doesn't appear on the right-hand side anywhere here. That's why people often just don't bother writing it down. What about epsilon? I've got epsilon on the right-hand sides, but I don't have an equation that tells me how epsilon varies in r. How would I find that, do you think? Equation of state, right? The equation of state, again, is going to be used to assume. So I'm going to assume that I can write something like this. Okay, some polytropic form that tells me how epsilon is related to p that allows me to close this set of equations. Another thing here is if I think about this equation, this looks like a Newtonian classical equation, right? You just want to know how much mass you have in a certain area. You just add up the energy or the mass density, multiply by r squared with 4 pi. That's what you'd write down in Newtonian physics. What do you think m represents? Actually, think about these two equations. That might be a better way. How are these two different? Because this one is the total number of particles within radius of r. And you can see I've got the number density here multiplied by the same geometric factor of 4 pi r squared, but I have something else here. This comes from the Jacobian of the metric, right? This, I think this is the Jacobian. It tells me how the volume elements, the proper volume as I go in r. This one really does mean the number of particles within radius r. Because this equation is missing this extra term here, this m is not the mass of baryons of radius r, but it actually contains what we call the gravitational mass. And so m of r is going to give me the gravitational mass. That means baryon mass plus whatever gravitational energy is there. Gravitational binding energy that's negative. And so m is the gravitational mass. And if I integrate all the way out to where r is to the total size of the star, then that total m would be the gravitational mass. If I take n and multiply it by the mass, okay, of each particle, that would give me the baryonic mass of the star. And it will be larger because it doesn't have any gravitational binding energy. And so sometimes when you look at star solutions, they will report both the baryonic mass and the gravitational mass, these two quantities that have that one has the binding energy, one does not. Okay? This afternoon you're going to solve this set of equations, and I'll give you a sheet of paper that has the equations in more detail. We'll talk about units and the specific equation of state. But I want to just kind of explain how you will start solving this. Okay? The way you'll do it is you'll basically guess or choose a epsilon or a rho, whatever, pressure at the center of the star. Okay, and then you'll calculate a P at the center of the star, P at 0. M is like the gravitational mass contained within radius r. At r equals 0, that would be simply 0, right? Because I have a point-sized object, I have no mass inside, and so that would be 0. N would be 0, right? If I have a point of 0 size at the center of the star, I have no particles contained in there. Phi I can choose to be whatever I want. Anyway, I would choose these initial values, and then I start integrating outward. Okay? And as I integrate outward, I'll see that the pressure will drop, and it will go down. And because for any stable equation of state, dp d epsilon has to be bigger than 0, otherwise the matter is not stable. The density will also go down, m will go up, and I'm going to keep integrating until I get to the edge of the star. How do you think we'll be able to know when we hit the edge of the star? When the pressure goes to 0, right? So the pressure will go to 0, and we just integrate until the pressure goes to 0. When the pressure goes to 0, we stop and we say, okay, that's the radius of the star. We check to see where we're at. That's the radius of the star. The little m evaluated at that radius will be the gravitational mass of the star. I can calculate the baryonic mass of the star, whatever.
Are we taking the pressure to be 0 at the center of the star?
No. This will be given by the equation of state. So I choose this to be something, this might be, if I choose it in terms of mass density, it would be something like 1 times 10 to the 14 grams per centimeter squared, cubed. And then I'll calculate what the pressure is. It will be a huge number, in the 30 dynes or something per centimeter squared. And then I'll integrate out until the pressure is 0, and then I stop, and that gives me my star solution. I can imagine doing this lots of times for lots of stars. And for every star, I can imagine plotting the central density. So I'm going to call this the central density of the star. Mass density. This is epsilon divided by c squared. This is where all these unit things come in. And this would be the total mass of the star. So I do this one time. I choose a central density, and I integrate out till the pressure is 0. I stop. I say, okay, what was the mass, gravitational mass of the star? And I would plot a point right there, right? And I'd have as a point. And then maybe I do that a whole bunch of times, and I kind of sketch out a curve that looks like this. Something like that. Okay? There's an easy way to tell whether or not these two solutions are stable. Remember when we wrote down the form of the metric, which I've erased, I assumed that it was static. There was no dynamics in time. And so this just tells me that I have a solution that's there. A different question is whether or not the solution is stable or not. And so there's a very simple stability test that you can do. And that is to look at the derivative of dm d rho c. Okay? Imagine, I'll just erase this point here. Imagine that I have a star that's at this point on the curve. Okay? And I imagine perturbing the star a little bit. Now let's say I perturb it kind of, I change the central density, I make the central density go up. Okay, so if I imagine taking the star, perturbing it a tiny bit, so that the central density increases, what happens to the total mass energy of the star? It also increases, right? So this is a condition or a perturbation that would be stable, because I change the central density, I increase it, the mass energy goes up. That's not something that wants to happen spontaneously. And so this star would be stable. If I look on this side, however, and I imagine taking the central density of the star and perturbing it, increasing it, now the total energy of the star actually decreases. And when that happens, this is something that can happen spontaneously, right? I perturb the central energy a little bit, and the total energy goes down. That's something energetically favorable. And so that will happen spontaneously. And you'll see that, as I go down to the next point, it's also got this negative derivative, and as I increase its density again, it's going to lower the total energy, which is energetically favorable, happens spontaneously. And so all of these solutions where d rho d, dm d rho c is less than 0 are unstable. Okay? And the solutions where it is positive are stable. Now this is a simple condition to apply, There is a more complicated way of doing it that always is true. This one is true most of the time. It actually over-predicts the number of stable solutions. These over here, for example, will turn out to be unstable. But anyway, I'm not going to worry too much about this. We'll just use this simple criterion, where if that derivative, as we calculate hundreds of these solutions, if that derivative is positive, we'll say they're stable. Where it's negative, we'll say it's unstable. Now, if we had an equation of state, a very nice, complicated equation of state, then that goes over many orders of magnitude here, we would find that these solutions could be related to white dwarf stars, and these solutions could be related to neutron stars, and these simply don't exist. Okay?
This makes sense because here also
yeah. The more exact stability criterion is related to the mass and the radius, total radius of the star, and it's a little more tricky to understand. You have to look at the derivatives of this, and you get these curves that kind of look like this. That's not a good example. It's these curves as you plot M and R. I don't remember what they look like. They come up like this, and then they swirl around. And it's the direction of the curvature that tells you something about the stability. And it's a more complicated criterion. And it turns out that these stars on this branch are in here, and this where the direction of the curvature hasn't changed.
So
this is more of a simplistic, kind of intuitive criterion. It works 2/3 of the time or something like that.
So even in this region where this derivative is negative, this is stable?
Oh, I'm sorry. These are also unstable. Sorry, I didn't mark those. Yeah. We can kind of think of it as there's just no matter here that has those properties there. We can create a gas of electrons that will support a white dwarf. At some point, the electrons can't support the mass of the star if you keep adding to it. And we have then a series of nuclear reactions that take place that turn it into a neutron star. And then when the neutron star can no longer support the mass, if we keep, say, accreting mass onto it, there's just nothing in nuclear physics left to change into that would give me another stability curve over here. But
This gives me
Quark stars, they would be there.
the quark stars are actually softer equation of state than the neutrons. And so when you add quarks to stars, you make it actually softer. And so quark stars are having trouble now, or equations of state are having trouble. Of course, we don't really know what the equation of state is, but with our guesses, they don't give stars heavy enough that have been observed. And so I think those, and when you go to, so other people have wondered about hyperons. Maybe the neutrons, there are other quark interactions that turn neutrons into hyperons, and these also soften the equation of state as well.
So given an equation of state, you can predict the maximum mass of neutron star.
Yes. Yeah, and so we'll do that. We'll give you the equation of state for a gas of neutrons, a gas of electrons, and you'll be able to plot these curves. And you'll be able to predict where the stable ones are. That's right. And if you write a hydrodynamics code, an evolution code, one of the first things you will do is you will generate these star solutions. And you will choose a star right here, and you'll put it into your code, and you'll make sure that when you evolve that star, it just kind of sits there and oscillates and doesn't collapse, and then you're happy. And then you'll choose one over here, and you'll want to see that star collapse. And that is one of the tests that you'll use to give you confidence that your evolution code is really working properly. So, okay? Okay, well, thank you. And I'll see you this afternoon and at lunch.